today, which is thermochemistry, energy, and chemical change. Okay. A little bit of technology problem, no DVD input, slow computer, so hopefully we can get this to actually work a little bit. How's that? Okay, so thermodynamics, energy flow and chemical change, which is chapter 6 again. So let's talk about thermodynamics and energy. So when we're studying reactions, right, so far we have looked at reactions as in terms of stoichiometry. How much can we predict? How much is required in a reaction? How much does that reaction produce as far as the products? What's the percent yield? That kind of thing. So studying reactions from that standpoint. Then we moved on to talk about the types of reactions and predicting products and writing net ionic equations. So writing equations that only focus on the participants in the reaction and so forth. We extended that to gases so that we could consider gaseous reactions. And now, as part of our study of reactions, we need to consider energy. Okay, so thermodynamics and energy. What we find is that energy transfer occurs or accompanies all chemical and physical changes. So anytime there's a chemical change, there's an energy consequence for that. Anytime that there is a physical change, there's an energy consequence for that. So even when we're simply boiling water, there's an energy change that's accompanying that. And so when we're studying chemical processes, okay, whether they are just physical changes or chemical reactions, it's important for us to consider what is the energy transfer that's happening during that process. It helps us to understand why reactions actually occur. And so this chapter introduces us to the study of the energy of reactions and processes. So first, some definitions. Okay. Energy is the capacity to do work. Okay, so we think about energy in lots of different ways, but energy is the capacity to do work, right? So our electronics are powered by electrons. Okay, that electrical energy, which is really kinetic energy, is allowing that work to happen. And then work is directed energy change that is resulting from a process. So energy is the capacity to do work. Work is the directed energy change resulting from a process. And when we're studying energy transfer in reactions, we have to consider both parts, right? We have to consider the work part is the system that we're studying, and it's really important for us to define what is our system and what is our surroundings. So we'll have to do that first. What is it that we're actually studying? Is there work being done on our system, or is our system doing work? Is there energy being transferred in that process as well? Many times we consider that just simply as heat. Is there a heat transfer that's happening as well? And so thermodynamics is just simply the study of energy and its transformations, considering what's happening during our processes and then studying those transfers. Particularly, thermochemistry deals with the heat part, and that's what we'll spend a lot of our time talking about in chapter 6, which is the heat part of that. And so what we typically try to do is we need to consider the energy in the work, but if we can remove the work component either by making constant work, okay, or making sure that no work happens, that the work can't happen, then all we have to worry about is the heat part. And so we really will boil this down a bit simpler to thermochemistry instead. I got two computers going, sorry. So when we're thinking about a chemical reaction, we tend to think about chemical reactions in terms of what are the reactants and what are the products. we're thinking about those in terms of atoms, okay, what are the atoms involved and what are the molecules involved in that process. If it's a redox reaction, we have to break that down even further because we have a transfer of electrons. So we've got to consider, okay, the electrons are being transferred, and so that's a consideration in our reaction as well. And so electrons can be a reactant in a product, particularly if we're breaking them down into half reactions. But now we're throwing in an extra part, which is energy. So we need to consider energy as part of the reaction. And what we'll find is that energy can be treated as a reactant. Okay? It is inputted into the reaction just like anything else, right? If we have calcium carbonate reacting with hydrochloric acid, those are the two reactants. But what is the energy consequence for that as well? Is energy being absorbed as the calcium carbonate reacts with the hydrochloric acid? And so then it would be a reactant, or is energy being produced? So in that production of calcium chloride and carbon dioxide and water, is energy produced? Okay, so is energy absorbed during the process, or is energy produced during the process? If it's absorbed, then we consider it a reactant. If it's produced, then of course it's a product of the reaction. Okay, it's gotten cold now, really quickly. Okay, so I spent fall break in Brown County, Indiana, and we were planning to spend a lot of time outdoors, and then it got cold. But when you're heating many times by a reaction, which is just simply burning of a fossil fuel, and the heat is a product of that reaction. So you're taking propane or natural gas, methane, something like that, burning it in oxygen in a redox reaction. You produce carbon dioxide and water, if that's a complete combustion, and heat. And then we use that heat. You probably drove here, or many of you probably drove here. We use the heat that is from the gasoline burning, so the heat is a product of that reaction, along with all the rest of the stuff that's produced in that reaction. So when we're studying thermochemistry and thermodynamics, we need to be really careful with definitions. Okay? Definitions such as system and surrounding. So what is the system? The system is what we're studying. Okay? The studied region when we're examining the thermodynamics. And we have to define this really, really carefully. The system can be really small. Okay, so if we're studying a chemical reaction, when we're studying chemical reaction, the reactants and products, that's the system. Now, it may be dissolved in water, but that water is part of the surroundings. Okay, so that we have to be really careful, because when we're studying the energy, we're considering where's the energy starting and where is it going. So is it starting in our system and going to the surroundings? Well, then it's really important for us to define these system and surroundings very, very carefully. So the studied region is the system. Okay, and again, it could be bigger, right? We could study global warming, okay, climate change, or whatever label you want to put on it. Okay, your system is the Earth and its atmosphere, and the surroundings is, well, everything else in the universe, right? So the surroundings is everything else. The system is what we're studying. The surroundings are everything else in the universe. And so we're considering, is energy going from system to surroundings, or is energy going from surroundings to system? Is our system gaining energy, or is our system losing energy, right? So the question of climate change or global warming is our system gaining energy overall, or is it not, right? So it's in some kind of equilibrium. There's energy being lost out into the universe, okay, at some rate, and when we add carbon dioxide to the atmosphere, that serves as a blanket and helps to keep some of that energy in, and so that's why we have that consideration. And so we've got to look at the system and surroundings. When we're studying a chemical reaction in particular, we're looking for the internal energy of the system changing, delta E or delta U. delta E energy, delta U work. Okay, so we're considering is the internal energy of the system changing during that chemical reaction or during that chemical process. And when we're looking at these thermodynamics, we had to be very particular. Okay, so when we're looking at a value in thermodynamics, hopefully you're to the point where you realize that a number is meaningless. A number has to have units that are attached. Okay, so that's particularly important here, because we need to know what the units are. It ought to have energy units, okay, joules or calories. But then we also have to have a sign. And that's not something we're used to putting on there, but with thermodynamics we have to put the sign, even if it's positive. Okay, it's better to put the sign because sign indicates direction. Okay, so is energy being transferred to or from the system into the surroundings? We're always taking a system point of view, always. Okay, so we're always taking a system point of view when we're looking at thermodynamics. And delta, of course, means change. Always means final minus initial. And so if our system is gaining energy, then the sign is going to be positive. If our system is gaining energy from the surroundings, then our sign for the system is positive. And again, we typically take the system point of view. We're always looking at it from what's happening to the system. And then if the system is transferring energy out, if the energy is going from the system to the surroundings, then of course that's a negative direction. So the surroundings is what's going to actually determine if the reaction occurs, and we'll talk about that later on. But we need to consider the system in most of these cases. So again, change is final state minus initial state. In reactions, this means products minus the reactant. So do the products have more energy or do the products have less energy? Okay. If they have more energy, then that's a gain. Okay. In order for the products to have more energy, they must have gained energy from the surroundings. It has to come from somewhere. Okay. And so we'll need to consider the change during this process. And so, sorry, I'm recording, and that's why I'm on two different systems here. Okay, so system and the surroundings. Okay, this is one from your book. We're looking at the energy of the system decreasing. So here's the initial state. This is the final state. So the delta E for the system, E final is less than E initial. Okay, it's always final minus initial. And so that means that delta E is less than 0. It's negative. Okay, so delta E can be negative. Negative just simply means that the final state is lower in energy than the initial state. And this is the most common case. Okay, it doesn't necessarily have to be this way, but the most common case is for the energy of the system to be decreasing. Most of our reactions actually give off heat, and there's a reason for that. Okay, the spontaneous processes have an energy that's going downhill. That's not to say that we can't have the energy of the system increasing, so the initial state is lower than the final state. So now final minus initial gives me a positive value, so E final is greater than E initial. And so that means that energy is absorbed from the surroundings, right? So if I'm looking at a delta E that's less than 0, what that's telling me is that during that process, the system lost energy, and so then it must have released it to the surroundings. That's what a delta E of negative means, less than 0. If a delta E is positive, however, that means that the final state has more energy than the initial state, and because of that, that means that energy must have been absorbed from the surroundings, right? We can't create or destroy energy. We're just simply transforming it or transferring it. And so the question is, are we transferring it or are we transforming it in this process? In this case, we're talking about transfer. So if the final state has less energy than the initial state, then the energy is released to the surroundings. This is what happens when you burn propane. This is what happens when you burn, well, any hydrocarbon, any single one of them. You burn a hydrocarbon, it gives off heat. Why is it giving off heat? Because the products, the final state, the carbon dioxide and water, are very stable molecules, and so they are in a low energy state, and that means that if they're in a low energy state, then energy has to go out. Okay? And that is a delta E less than 0. So again, define very carefully what your system and your surroundings are so that we can study these very carefully. Heat and work. Okay, heat, which is given the symbol Q, and you'll want to know that later. It'll simplify things when you start doing calculations. It'll ask for heat or heat transfer or something like that. Heat is given the symbol Q. And so what we're trying to do when we're studying thermochemistry many times is we're trying to find Q. What is the Q for the reaction? What is the Q for the process? Okay. Is heat being absorbed? Is heat being given off? And so Q is the transfer of thermal energy between two bodies at different temperatures. Okay. And again, it does not have to be. I tend to use examples that are chemical examples, but this could be a physical as well, or there may not be even any physical change at all. This, of course, is related to temperature. So what is temperature? Well, temperature is related to heat, but temperature is simply the measurement of an object's heat energy content and its ability to transfer the heat. So think about temperature as the ability to transfer heat from one object to another. So we're thinking about energy transfer, okay, we think about it from a reaction or process standpoint. Is the final higher or lower than the initial, but then we have to consider, okay, so what's happening to the temperature? Is the thermal energy higher or greater at the beginning and end of this process? And so if we're thinking about temperature, it's the ability to transfer heat. So what direction does it transfer? The transfer is always from a high temperature to a low temperature, always. Heat transfer is always from high temperature because high temperature means it has more energy content, sort of, but it has a greater ability to transfer heat. If it has a higher temperature, it has a higher ability to transfer heat. And so it's always from high temperature to low temperature. And so that's always the direction, which raises some interesting questions when we start thinking about these things. Okay. For instance, why do you put ice in your tea? Why do you put ice in your tea? Because you want it to be cold, right? You want your tea to be cold, but really, what you want to happen, you want your ice to be warm. Wait, what? Yeah, what? Why do you put ice? What's the direction of the energy transfer? It's not from the ice to the tea, it's from the tea to the ice, right? And so what you're doing actually is you're warming up the ice. Now yes, it does decrease the temperature of your tea, but what you're really doing is you're warming up the ice. That's what's really happening, because the energy transfer is from the direction of the tea to the ice. Okay, so we got to be really careful when we're thinking about these things. Higher temperature means higher ability to transfer heat. So heat is always moving from hot to cold. Higher temperature hot substances are always transferring to cold substances. And that will happen until they reach the same temperature. Right? The hot object is always transferring heat energy to the cold object. And that will happen until they reach equilibrium, right? So you're putting your ice into the tea. The tea is transferring heat energy to that ice, and it will continue to do that until they reach the same temperature. Now, what you plan on doing in most cases is adding so much ice that there's still solid there, and so it stays cold for a period of time, right? You want the ice to remain so that the tea continues to transfer as the tea absorbs heat from the surroundings, right? Because the surroundings is warmer. Surroundings outside the glass is warmer, and so that's transferring heat energy into the tea, and you want the tea then to transfer the heat energy into the ice to keep it cold. And so that's the direction of the transfer, because the heat is always moving from hot to cold. Okay. How do you measure temperature? Well, you measure the temperature with a thermometer. How does a thermometer work? Mercury thermometer. What happens? Yeah, so when you put the thermometer, let's just say you're putting it in your mouth. Okay, you put that thermometer in your mouth. What happens? Well, the mercury rises up inside the glass tube. Why does the mercury rise up inside the glass tube? Because it must be expanding, right? Why is it expanding?
Heating up.
Because it's heating up, right? So what's happening? You put it in your mouth. Your mouth is at a temperature. It transfers heat energy to the glass. And the glass transfers the heat energy to the mercury. And then both the glass and the mercury expand. It's just that the mercury expands a whole lot, right? That's why we use, in the best thermometers, we use mercury. Why? Because it expands a lot when it's heated. So you raise up the temperature, it expands a whole lot because the mercury atoms are moving a lot more. And that expansion rises up the tube, and we just calibrate how high it moves inside that glass tube. So that's temperature. The amount of heat or the thermal energy depends on both the temperature and the amount of substance. The amount of heat energy, so we have two things that we've got to consider here. One is the temperature, right? Because the temperature gives us an idea of what's happening, what is the ability to transfer heat energy. But that's an incomplete picture, because we actually need to understand also the thermal energy that a substance has. The thermal energy depends on the temperature, so how hot is it, but also the amount of the substance. Okay, so an example I like to give is you have a cup of hot coffee, and then you have a bathtub that's filled with water. And the water is, let's just say, room temperature, so it will feel cold when you get in. Which one has more thermal energy? Well, which one do you want to put your finger in? The bathtub or the hot cup of coffee? Bathtub. You gonna stir around the hot cup of coffee with your finger? Not from Starbucks, probably. Why? Because it's hot. Okay. And that is a reference to hot means temperature, right? Hot means temperature, right? So why don't you stick your finger in and stir with your finger? Because the temperature is high. Because that liquid, that coffee inside the cup, has a really high ability to transfer heat to your finger, and it hurts. It starts to cook your finger. But the bathtub has more thermal energy. How can it have more thermal energy? because the thermal energy is related not just to the temperature, but to the amount of the substance, right? There's so much more water, even though it's at a lower temperature, because there's so much more, it has more thermal energy, right? So when we're considering these transfers, and particularly when we're studying the transfer, we're going to be measuring the temperature, because the temperature tells us, okay, what's the direction of the flow, which one has more heat energy to transfer, and so forth. But then we ultimately have to come back to the thermal energy. How much thermal energy is in this substance? Because the amount actually matters. And so when we're measuring heat, heat is going to be a function of the temperature, but also the amount of the substance.
What if you're taking a steaming hot shower?
You're taking a steaming hot shower. What do you mean?
Steaming hot shower instead of the bathtub. Instead of the bathtub.
Okay, so the steaming hot shower, if it really is steam, what's the temperature of the steam?
Really hot.
Really hot, okay? And so, why don't you cook? Right? You steam vegetables. Why do you steam yourself? First off, the temperature's not quite that hot, okay? But the steam, there's a relatively small amount of water there, right? So that steam is transferring thermal energy to you, but because there's so little actual water, mass of water there, it makes you feel hot, but it's not actually transferring that much energy. It will burn you if it's really steam, okay, as opposed to just water vapor. Right? So that steam coming out of the kettle, okay, will scald you, will burn you. Okay, so when you're we need to consider both parts. Amount of heat, the thermal energy, and the temperature, okay, when we're studying these reactions. Now we have to consider work as part of this as well. Right? So it's not just thermal, although we'll tend to focus on the thermal heat part, the Q part. We have to also consider the work part. The work is the transfer of energy through movement by force. That's the work part. And if our system is doing work, okay, that's part of the energy component, right? When you have your internal combustion engine running in your car, right? You're not just concerned about the heat part. You know, on a cold morning, you're waiting for that thing to warm up, right, to pump out heat to you. But that's not the primary reason that you're running the car, right? You're running the car so it does work, right? So when that reaction is happening, we want to consider the heat part, but we also want to consider the work part as well. And the work is just a transfer of energy through movement by force. And so the energy change, the delta E, is the Q part plus the W part. The Q part plus the W part. The heat plus the work is the delta E. So when we're considering the energy change for a process, we've got to consider both parts. And sometimes our setup is such that we can neglect one or the other, typically the work part because it's more difficult. Let's talk a little bit more about energy transfer. If the energy transfer is heat only, then heat is taken in or released. I've already talked about that. Some labels here are definitions. Systems that release energy are called exothermic. Systems that release thermal energy, release heat energy, are called exothermic. Okay, so exothermic means release. into the surroundings. Again, we're taking a system point of view. So we take a system point of view. From a system point of view, if the system point of view, the system is losing heat energy, then that heat energy has to go somewhere. It's going to the surroundings, and we call that exothermic. That's what exothermic means. Transfer of heat energy to the surroundings. And the Q then, because we're talking about heat here, the Q then for the system is less than 0. That's what exothermic means. If your Q is less than 0 for the system, your Q is less than 0 for the system, that's called exothermic, and that means that energy is transferred from system to surroundings. And then the delta E is less than 0 if we're talking about heat transfer only. The delta E would be less than 0 as well, right? Because we're controlling for the work, either allowing no work to happen or making it constant. Systems that absorb energy are said to be endothermic. So that's exactly the opposite. Q of the system is greater than 0, and so the delta E is greater than 0 as well. So again, we're taking a system point of view. Endothermic means heat is coming in. So during that process, heat is entering the system. Final is more energy than the initial, and so Q is greater than 0 and delta E is greater than 0. That's what endothermic means. Exothermic means transfer out, exo out, endo in. And again, from a system point of view. So what do we observe? You have a process that's exothermic happening in a beaker. Magnesium reacts with hydrochloric acid. When it does so, it produces hydrogen gas and magnesium chloride and heat. So heat energy is a product. What's going to happen when you grab that beaker? It feels hot, right? Why does it feel hot? Why does exothermic feel hot? It's releasing energy to the surroundings, right? And when you grab hold of it, your hand is part of the surroundings, right? And so it's transferring heat energy to your hand, and you feel that as hot. Right? And so endothermic is exactly the opposite, right? That system is absorbing energy. And so when you grab hold of that one, it feels cold, right? It feels cold, and the reason it feels cold is because your hand is part of the surroundings, and it's absorbing heat from the surroundings into the system, and so it feels cold. And so we can monitor these by monitoring the temperature. We have to be careful because when we're monitoring the temperature, almost always we're monitoring the temperature actually of the surroundings and not of the system, right? When we do thermochemistry, we plunge our thermometer down inside the container, and we say, oh, I'm measuring the temperature of the system. But no, what you're actually normally doing is measuring the temperature of the surrounding. So you say, okay, but it's inside a coffee cup, or it's inside a beaker. Isn't my system what's inside the beaker? Well, this is why we have to define very carefully what is actually the system and what is the surrounding. Because the system, many times, is the actual reactants reacting to form products. They're in a solution, and you measure the temperature of the solution, but the solution, the water part, is actually part of the surroundings and not part of the system. And so that's why we have to be really careful when we're doing these definitions because when we're studying them, we're going to study them many times by measuring the temperature. And where do you put the temperature? The temperature probe, the thermometer or temperature probe. Is it part of the surroundings or part of the system? So we have to be really careful how we define these. Okay, so if you have a beaker that has hot water in it, say boiling water. Well, let's say it's hot water just below boiling. And you just let it sit around until it reaches room temperature. What's happened? Because it's hot, high temperature, it transfers heat from the water, which is the system, to the surroundings. Okay, and so in that case, our delta E is decreasing, right, because we're considering the water. And so Q, heat energy, is released to the surroundings. On the other hand, we have ice water, so ice cubes in water in a beaker. You'll let it sit around for a while, and it eventually reaches room temperature. So from the standpoint of the water inside that container, it's absorbed heat energy from the surroundings to reach room temperature, right? So the thermal energy here to here, right, we see that as a decrease in temperature, but the thermal energy has decreased going from hot water to room temperature water. And so that means heat is released to the surroundings. Delta E is less than 0 for the system, which means that delta E is greater than 0 for the surroundings. On the other hand, if I start with ice water and go to room temperature water, then this is a lower thermal energy to higher thermal energy. Okay, because if we assume the only difference is temperature, right, the amount of water stays the same, then that's an increase of heat from the surroundings. Q then is greater than 0 for the system, but Q would be less than 0 for the surroundings. If we consider work transfer, okay, so that's heat transfer, and that tends to be the place where we focus more commonly. If we look at work instead, we're considering is work being performed by the system on the surroundings, or is work being performed by the surroundings on the system? That's our question. Okay, so a common way to produce hydrogen gas is this reaction. Zinc metal reacts with hydrochloric acid. Okay, zinc is an active metal, so it will react with acids like hydrochloric acid to produce zinc chloride and H2 gas. So gas is being produced inside that container. If we have a sealed container, then the evolution of the gas can manipulate the surroundings. And so the question is, does gas do work on the surroundings so that the work for the system is less than 0, right? This is gas doing work on the surroundings. Work is being, the work of the system is less than 0 and delta E is less than 0. Or on the other hand, the surroundings can do work on the gas. So from the system's point of view, again, the work is greater than 0, and so delta E is greater than 0 as well. And so just to try to do this pictorially so you can see a little bit what's happening here. It's a little bit small. Here's our hydrochloric acid plus zinc inside a container. Okay, it's sealed. Okay, so you have this inside a metal container or a sealed glass container with an outlet on the top, and that outlet has a plunger. Okay, so it's like a syringe but has a plunger on it, and the plunger is movable. So it's a movable plunger. When the hydrochloric acid reacts with the zinc, it produces H2 gas. Excuse me. Produces H2 gas, which can then move the plunger, right? As you increase the pressure inside the container, then that plunger can move. Okay, and so that is work being done on the surroundings. Work being done by the system on the surroundings. And so work is less than zero. Okay. On the other hand, you have this case, you have a trap gas, again, movable piston. If you move the piston to compress the gas, then that means that you are doing work on the system from the surroundings, right? Because you are compressing the gas. And so because work is done on the system, the work from the system's point of view is greater than zero, and delta E is greater than zero. Okay? We'll look at this work many times as pressure volume work. And so what we're considering is, what's the change in volume, what's the change in pressure for the system versus the surroundings, right? So if the plunger is moving, the system is pushing that plunger, that is work being done on the surroundings. On the other hand, if we push on the plunger to compress the gas, then that is a work being done on the system by the surroundings. And so the W is greater than zero here, whereas W is less than zero there. And so we've got to consider both parts, particularly when we have gases produced. And so just to kind of summarize, sign conventions and delta E. Okay, because this is what it's going to come down to when we're studying these reactions and processes. It doesn't have to be a reaction, it could be a process. Is heat being absorbed or is heat being released? If heat is absorbed by the system, okay, and notice it's always from the perspective of the system. Is heat being absorbed by the system or is heat being released by the system? If it's absorbed, then the sign of Q is plus. If it's released, heat is released, then the sign of Q is minus. So from the system point of view, is energy coming in? That's an absorbed. From the system's point of view, is the heat, is the Q going out? And then the work being done on the system, plus and plus, okay, or if the work is done by the system, minus and minus. And so then for our delta E, because it's a combination of Q and W, right, if they're both plus, that means energy is absorbed. If they're both minus, that means energy, the delta E, is released. If there's a mixture of the two, as we would expect, right, if heat is absorbed but work is being done on, right, plus sign plus a negative sign, then the delta E depends on the sizes, right? If W is larger, then it's negative. If Q is larger, then it's positive. We'll stop there. Continue on with chapter 6 next time.